what I'm going to present are essentially two talks smushed into one. One is going to be a summary of the book that I wrote about the origins and evolution of bipedalism. And then I'm going to dive more into the research that I've been doing at a very famous footprint site in Tanzania known as Laetoli. So as Kenny mentioned, my name is Jerry DeSilva. I'm a professor at Dartmouth College in New Hampshire, snowy New Hampshire. We're getting hit with a lot of snow right now. It's actually quite beautiful. I grew up in Massachusetts. I was a New Englander. I've always loved science. I thought I was going to be an astronomer, actually. I went to school to study astronomy, and then just sort of bounced around the different sciences, biology, and it wasn't until after college that I discovered my passion for human evolution. I worked at a science museum. I worked at the Boston Museum of Science and fell in love with teaching science, fell in love with mostly informal science education. And then kind of discovered by happenstance paleoanthropology, which is the study of humans. Anthropology study humans, paleo study fossils, so fossil humans. And to me, they just give us this remarkable insight, not only into our evolutionary history, but each of the fossils that we find is of an individual. And bones are these like little time machines that we can use to reconstruct the life of the individual. So you're not only learning about how these individuals lived their lives and eventually died, but how each of those individuals pieced together tells us the story of how we got to be the way we are today. And in particular, what I'll focus on is this really strange aspect of the human condition, which is upright walking. The way I like to start talks like this is to sort of just have everyone deal with the fact that we're weird. That humans are a weird mammal. There are so many things that we share in common with other primates and other mammals, and particularly other apes, but we are strange. Even though we're mammals, we have very little body hair. We have exceptionally large brains for our body size and have developed complex cultures. While other animals communicate, we can talk, right? Many animals pant to dissipate body heat, but we sweat. But perhaps oddest of all, I would say, humans navigate their world on 2 rather than 4 legs. We are bipedal. So this evening, what I'll do is I'll cover some of the material that's in a book that I wrote on this topic called First Steps, which examines the evolutionary history of bipedal walking. And it explores how this form of locomotion, to me, was the gateway for many of the changes that make us human. And then in the second half of the talk, as I mentioned, I'll take you to the fossil site of Laetoli, Tanzania, where we're making some really, really fun discoveries that have actually complicated what we thought we knew about the evolution of upright walking. So just to take a step back and contextualize this, DNA studies have demonstrated quite clearly that humans are most closely related to the African great apes, and in particular to chimpanzees and to bonobos. And of course, this doesn't mean that we evolved from chimpanzees any more than they evolved from us, right? They're our cousins. Our lineage and theirs diverged from a common ancestor that lived about 6 million years ago. Now, one of the things I like to do with students is to sort of say, okay, 6 million years, how long ago is that? Well, assuming that a new generation appears every 20 to 25 years or so, the last common ancestor that I shared with a chimpanzee was my great-great-great-great-great-great-great-great-great-great-great-great-great-great-great-grandmother with about 250,000 greats in front of grandmother. Another way to think of it is if I said great once a second, it would take me 3 full days without a break to reach the point where my lineage diverged from a chimpanzee's. So we can do some science now, right? We can say, if this was true, if humans and chimpanzees share a common ancestor, then we should find fossils of things that were neither human nor chimpanzee, but had some characteristics of both and had some unique characteristics as well in African sediments going back 6 million years or so. Now, a lot of folks call these the missing links. I'm not a big fan of that term because many of them aren't missing at all. We literally have discovered thousands of fossils of ancient humans. And the word we use for these is hominins. We call them hominins. And shown on the screen right now are some of the most famous. You can think of them as kind of the greatest hits. So there's Lucy, and there's Artie, and there's Nereocotame. And Sedib is there. Naledi's not even there. You'll hear about Naledi in a couple of weeks. No, there is no. Okay, Naledi is there. I just spotted it. So there are some really wonderful fossils here, but there's so many more that we've discovered. And as a scientist who works on this, what I can tell you is that every single fossil we have, whether it's a partial skeleton or a tiny little fragment of a shin bone, each one of these fossils is important. And it tells us an important story about us and how we got to be the way we are. These fossils are all that remain of once breathing, thinking beings who laughed and cried and lived and eventually died. And I see them as remarkable gifts that we have to help piece together the story of how we became human. Now, with all those fossils, it helps to sort of think about a general framework. And the general framework of human evolution is well established, but it's pretty complicated. And every time we find new fossils, it forces us to reassess some of our old ideas, which is how science works, right? Now, if we go back to the beginning of our story, 6 million years ago or so, long before any evidence for stone tools or controlled fire, before we see evidence for brain enlargement, before language, before art, our ancestors evolved the ability to walk on just 2 legs. So what got us started on this remarkable human journey was the way we move. Now, how do we know this? We know this because we've got fossils, right? The very oldest fossils we have that are hypothesized to be on the human lineage or have been argued to be on the human lineage. Why do we think they're on the human lineage at all? Is because they show hints and evidence of upright walking. These have been recovered from ancient sediments in Africa, in Chad, Kenya, and Ethiopia, and they preserve anatomies that they share in common with us. And these anatomies we think are biomechanically linked to this ability to hold your body in an upright posture and even move, propel yourself 1 leg at a time. So we're going to come back to the fossils in just a bit. But for now, just understand that walking on 2 legs is ancient. And it is the most ancient defining characteristic of our hominin lineage. But from an evolutionary perspective, we take a broader sort of comparative and evolutionary perspective, it's a really strange way to move. It's an odd way to move as a mammal. There are mammals that fly, swim, cling, and leap, mammals that swing, sprint, knuckle walk, and climb. There are also mammals that hop, right? Those are bipeds too, but I'm going to be focused on just the ones that stride 1 leg at a time. And then look, most mammals do what the cow in this picture is doing. They move around on just all 4s, similar to, say, a goat or a sheep, a horse, dog, cat, squirrel, you name it. And that's the way you move for most mammals, right? But not us. We move on our extended hind limbs, and it's a really strange way for a mammal to get around. And here's how strange. In a typical lifetime, the average non-disabled person takes about 150 million steps, and that's enough to circle the Earth 3 times. But we don't think much about it. If I posted a video right now of myself walking, I can't imagine many people would find it interesting enough to watch. However, watch this video. This YouTube clip of a bipedal bear named Pedals, who is moving on 2 legs through a New Jersey suburb, has been viewed now almost 7.5 million times. Videos of Pedals ended up on the CBS Morning News. So when a human walks, right, we have a word for it. It's pedestrian, right? It's ordinary, it's average. We don't really think about it. But when another mammal moves on just 2 legs, it ends up in the news, right? It's a newsworthy thing. Bipedalism has made its way into our words, our expressions, our entertainment. Think of the many ways we describe walking. We stroll, stride, plod, traipse, amble, saunter. We shuffle, we tiptoe, lumber, tromp, lope, strut, swagger. After walking all over somebody, we might be asked to walk a mile in their shoes. Heroes walk on water, and geniuses are walking encyclopedias. To humanize an animated character like Winnie the Pooh or Brian from Family Guy, who's a dog, they're drawn as bipeds, right? And think of the joy we experience watching a child's first steps. The Dutch master Vincent van Gogh captured such a scene in 1889. And a century and a quarter later, this is my own kid taking some of their first steps. I love this video. My kid's now 12. So it's been a while. There've been lots of steps. Once kids start walking, they don't stop. A couple of years ago, I visited Karen Adolph's developmental psychology lab at NYU, and she's fantastic. And in her lab, a toddler followed this path that you see right here, traced out in blue, in just 10 minutes. The average toddler takes 2,368 steps, which is the length of 8 football fields, every waking hour. And that's how they learn how to walk. So Karen Adolph has written that the way they learn how to walk is thousands of steps and dozens of falls per day. But moving on 2 legs is more than getting from point A to point B. It's a form of communication and identification. So my wife and I both work at Dartmouth. That's kind of what it looks like now with the snow. And I can occasionally spot her striding across the campus green, or campus white in this case. And I know her just from her walk. Even when I'm too far away to see her face, just from her cadence and her posture, I can tell it's her. And from her cadence and posture, I can tell if she's in a good mood or if she's had a tough day. Each of us has our own unique personal gait, and humans are particularly fine-tuned to identify individuals from their walk. And we can ask the question of why, and there are some suggestions that gait and posture cues might have been critical means of communication in our pre-verbal hominin ancestors. And not only that, but there are physical and mental benefits to walking, as many people know. There was a 2012 study done by the National Cancer Institute, and it was done on 650,000 people. And they found that individuals who did the exercise equivalent of a 25-minute daily walk lived on average 4 years longer than more sedentary counterparts. 4 years. A daily walk has been shown to improve memory and creativity. It helps ward off certain cancers, diabetes, stroke, and cardiovascular disease. But of course, this isn't magic. There's a physiological mechanism behind it, and it's being figured out, starting with work done by Danish physiologist Bente Klarlund Petersen. She and her team discovered that your muscles act as endocrine organs, which is so cool to think about, muscles as endocrine organs. And they release molecules called myokines into the bloodstream when they contract. So these myokines target organs throughout the body, helping maintain health. And it's not that walking is some cure-all, though. As somebody who studies human evolution, I see this somewhat differently. Walking is our default. It's what we've always done. Throughout our history, if we wanted to eat, we had to walk. So what's new for humans, many humans, is not walking. And that immobility has had a huge impact on our collective health. Now, I do recognize that this can be complicated. Having the opportunity to take a walk safely and without harassment or worse is a privilege not afforded to everyone as long as racism and sexism persist in our society. But taking a walk and the biological ability to do so is important, and it always has been. Upright walking, I'll argue, set in motion all of the major evolutionary events in the human lineage. It happened first, right? It set the stage for everything that followed, from dietary changes and freeing the hands to create and use stone tools, to cooperative parenting, eventual brain enlargement, language, the development of trade networks, allowing us, eventually, a once humble ape standing in ancient Miocene forests, to populate the globe. Despite this, though, and what's kind of fun as a scientist who studies this, we still aren't sure why upright walking evolved at all. There are hypotheses about bipedalism evolving to carry food or to carry babies. There are some researchers who have posited that upright walking was energetically beneficial to our ancestors, and that's why it took hold. There are ideas that uprightness helped our ancestors see over tall grass, pick low-hanging fruit, or even wade through water. And of course, there's the ever persistent but incorrect, there's no evidence for this at all, incorrect idea that ancient hominins stood on 2 legs to wield weapons. This is the so-called killer ape idea, made famous in Stanley Kubrick's science fiction thriller 2001, A Space Odyssey. Now, okay, I'm sure you're all familiar with this image, right? Or this one, or this one. This sequence, which is called the March of Progress, appears everywhere, right? It appears on t-shirts, coffee cups, bumper sticker. You Google human evolution, this is the kind of thing you see. And it always assumes that upright walking hominins were kind of early ones were hunched over, having evolved from a chimpanzee-like knuckle walking ancestor. But the fossils, and my interpretation of the fossils, is that this may not be right either. In fact, we still aren't even sure the body form from which upright walking first evolved. There are some researchers who have proposed that instead of bipedalism evolving from the ground up, it happened from the trees down, from an an ancient ape in the Miocene, standing or swinging in the trees, right? And this is something that I think is consistent with the fossils we have. Now, to test these ideas, we need more fossils, right? Particularly skeletons from 5, 6, 7, 8, 9, 10 million years ago, the key window when these changes were taking place. However, those skeletons are yet to be discovered. We will, but we haven't yet. What we have instead are tantalizing fragments, a skull here, a femur there, a toe bone. But in paleoanthropology, you work with what you have. So let's look at what we have. All right. The most relevant partial skeletons that we have to address the question of what did we evolve bipedalism from? They've been announced to the world in just the last decade or so. Ardipithecus ramidus, this is Ardi, a 4.5 million year old hominin skeleton from Ethiopia. So this is over 1 million years older than the famous Lucy, first published in 2009. And a skeleton called Udo. Now, Udo is from a species that's been called Danuvius guggenmosi. This was discovered in 2019 by Madeline Burma. Now, Udo was found in Germany, and it's 11.5 million years old. And you heard that right, Germany. 11.5 million years ago, there were vast forests around what is today the Mediterranean. And ancient apes today live in Africa and live in Southeast Asia, but apes at that time lived in those forests around the Mediterranean in Southern Europe. So we find fossils of ancient apes in Spain, France, Italy, Greece, Turkey, Hungary, and even Germany. So even though we don't have the skeletons from the exact time period of the last common ancestor that we share with chimpanzees 6, 7 million years ago, we have these two skeletons from 4.5 and 11.5 million years ago. And I sort of think of them as the bookends to the story, even though they're not necessarily the story itself. Eventually we'll have those fossils because every year we find more and more. I was just talking to John about some more fossils just a moment ago. But for now, we can ask the question of, can we still learn something from these bookends? And I think the answer is yes. What they tell us is that there's no evidence of knuckle walking in these creatures at all. These skeletons suggest to me instead that our imagery needs to change, that the common ancestor of humans and the African apes may not have been a knuckle walker at all, but an apes moving on two legs up in the trees, something that orangutans, gibbons, and spider monkeys sometimes still do today. Now, if that turns out to be the case, then we no longer have to come up with an explanation for why bipedalism evolved from some knuckle walker, because it didn't. It wasn't a new locomotion at all, just an old locomotion in a new setting. One of my colleagues, Carol Ward at the University of Missouri, has said that asking why humans stood up from all fours is the wrong question. Perhaps we should instead be asking why our ancestors never dropped down on all fours in the first place. Now look, it'd be foolish of me to think we have this all figured out. There could be fossils that are going to be discovered in the next decade that show that we did evolve from a knuckle walking ancestor. That's fine. As a scientist, you always have to be willing to admit that what you thought at the moment is wrong when new evidence emerges. So there's a whole lot of this story still to be discovered and still to be written. But for now, I think we need to entertain this possibility that this knuckle walking ancestor didn't exist. But still, it's a wonder we're here at all. We humans are pathetically slow. Even the fastest human to have ever lived, Usain Bolt, shown here, right, maxed out at 28 miles an hour during his world record 100-meter dash in 2009. 28. That's half the speed of a typical galloping quadruped of our size, a zebra, an antelope, a leopard, or a lion. So he couldn't have caught an antelope, and he certainly couldn't flee from a lion. And in fact, there are 2 leopard fang holes in the back of a head of an ancient human fossil discovered in a South African cave. And these are a gruesome reminder that there were evolutionary consequences for our lack of speed. And not only that, but the short, squat pelvis that biomechanically adapts humans for efficient bipedal travel also forces a baby to corkscrew through the birth canal during delivery, making childbirth difficult and sometimes dangerous. We are also unstable on our two legs. We fall all the time. When's the last time you saw a squirrel or a cat or a dog trip and fall? So I'm making light of this, but 30,000 Americans and 500,000 people worldwide die from falls every year. And as we age, bipedalism takes its painful toll on our backs, our knees, and our feet. Bipedalism not only leaves us vulnerable to leg and foot injuries, but it makes us particularly feeble when they happen. Now look, the advantages of bipedal locomotion obviously outweigh the costs. Otherwise, we would have gone extinct long ago. But given the many downsides to upright walking and how rare this form of locomotion is in the animal world, the mammalian world, I've wondered what tipped the scales towards survival rather than extinction. And the answer, I think, might be found within one of the most wonderful and mysterious aspects of the human condition. It's rumored that an anthropology student once asked Margaret Mead for the earliest evidence of human civilization. And after a brief reflection, Professor Mead responded, "A healed femur." Now, this exchange is likely apocryphal, I've learned, but the point remains, I think. So I wonder then what she would have thought of this awesome fossil from Kenya. It's a 2 million-year-old hominin femur with a healed fracture in the shaft, healed fracture. Or this one. This is another 2 million-year-old fossil from Kenya. This time it's a small shin bone, preserving evidence of an ankle fracture. Again, though, a healed one. Or this fossil. This is an even older 3.5-million-year-old partial skeleton discovered in Ethiopia by Johannes Haile Selassie, who you'll hear about again in a moment. It's from Lucy's species, Australopithecus afarensis, and this is a large male, we think, nicknamed Katanumu, which means big guy in the local language. And he too broke his ankle when he was a kid, but it healed and he lived into adulthood. So I need you to think about this for a second, right? Long before hospitals and doctors, long before fire and shelter, our already slow and unstable ancestors living on a dangerous landscape littered with large carnivores that wanted to eat them were occasionally breaking bones and surviving? To me, this means one thing, that they were helping each other out. I think we've had each other's backs for a very long time. Bombarded in our 24-hour news cycle with examples of human cruelty, we often overlook how remarkably cooperative and tolerant we can be. Helping one another comes naturally to us. Holding a door open for a neighbor, donating spare change, passing a plate to share food with others. These are such everyday occurrences that human kindness, kind of like walking, has become pedestrian. I think it could be that one of the most mysterious aspects of the human condition, our capacity for selflessness, arose out of our vulnerabilities as bipedal apes in a dangerous world. These behavioral changes that accompanied the evolution of walking are not just important for those who can walk, but also for those who cannot. As descendants of bipedal hominins, our evolutionary journey continues because empathy, cooperation, and generosity evolved in lockstep with our distinctive form of locomotion. After millions of years and dozens of evolutionary experiments, we humans are now the last bipedal ape on Earth. And as we stride forward as a species into really uncertain and unsettling times, I do think paleoanthropology is a nice lens to think of ourselves through. It helps us to glance back over our shoulder at the trail we've left behind. We've traveled far and overcome a lot, and we've done it together. Now, this image here is from fossilized footprints, and it's a good way to transition into the second half of my talk. These footprints were discovered at the site of Laetoli in Tanzania. They're 3.5 million years old. They are the oldest uncontested evidence for human-like upright walking in the fossil record. We argue a lot as scientists about the shapes of fossils and the shapes of bones. You can't argue with footprints. These footprints show very clearly something moving on two legs. The site of Laetoli, where I do a lot of my work each summer, is in northern Tanzania. It's just east of the Serengeti and west of the Ngorongoro crater. and it's south of Olduvai Gorge, where the very famous paleontologist, the Leakey family, did a lot of their work in the 1950s, 60s, and 70s. After Louis Leakey died, however, Mary Leakey, who had been told about this site from Maasai who live in the area and had actually visited the site years earlier, moved south to Laetoli and established a new research project at this, what she thought and was right, an older fossil site at Laetoli. And Laetoli has one of the greatest sort of discovery stories in the history of our science. One of these really serendipitous moments that happened on July 25th, 1976. There were a number of visitors to the site, and they were walking around looking for fossils. And one of them, David Western, shown on the far left, got a little playful, and he picked up a piece of dried elephant dung, and he chucked it at the others. And of course, they didn't want to get hit with elephant poop, right? So they took shelter and they found some more elephant poop and threw it back. And so this game of elephant poop dodgeball starts. And Andrew Hill and Kay Berensmeyer didn't want to get hit. So they jumped down into a gully. And in that eroded gully, what they spotted was that the gully had eroded enough overlying sediment that it exposed this layer of volcanic ash, hardened volcanic ash, that preserved in it fossilized footprints of elephants and even fossilized raindrops. So fossil footprints are amazing. So they stopped the game, right? They said, okay, no more elephant poop. They called everyone over. And when they called folks over, they realized that this is a pretty awesome discovery, right? And so they clear the area, and this is an area that's now known as Site A. It was the first one discovered, so Site A. And at Site A, they discovered upwards of 17,000 footprints. These are footprints of antelopes and zebras, footprints of rhinos, footprints from giraffes and ancient elephants, leopards, even little millipede footprints. And Mary Leakey said, hey, be on the lookout, because they were finding fossils of Australopithecus, be on the lookout for something moving on two legs. And later that year, indeed, they did find fossil footprints of something moving on two legs. You can see that on the screen right now, circled in red. We've got a right foot, a left foot, right foot, left foot. These footprints are really strange, though. Their proportions are kind of off. The gait is weird. It's an individual actually cross-stepping like a model on a runway. And Mary Leakey had a hard time convincing her colleagues that these were from an early hominin. And they kept searching, though. And 2 years later, they discovered one of the most famous collection of remains in the history of our science. And those are the famous G prints of Australopithecus. These were discovered in 1978, and they're undoubtedly from an early hominin. This is an upright walking individual who has a foot that's a lot like yours and mine, moving on two legs, a lot like you and I would do. There are, we think, 3 individuals making these prints. There is a smaller individual on the left and 2 individuals, the second of which walking in the prints of the first, that are making that trackway to the right. This is kind of a cartoon version of what happened. So with the cursor, hopefully you can see it. You've got left, right, then there's erosion, you lose some of it, and they're moving to the north. In fact, most of the animals, this is a study we have in review right now, most of the animals are moving in a random way, but the hominins are all moving to the north. And we think there's water there. We think that the Olduvai Basin would have had a lake, and they know that. They know that this is, in a sort of a volcanic ash choked area. They wouldn't have been able to get water easily, and they're moving to the north. So there they go, left, right, left, right, left, right. And 2 things that I want to mention about them. The first is when the American Museum of Natural History was going to do a diorama to teach this in their museum, they had individuals who had feet of the correct size, of the same size as these 2, walking side by side. And what they found was that they couldn't actually walk without hitting shoulders with one another. And yet the footprints themselves are stunningly coordinated. So the only way to get the 2 individuals to walk in a coordinated fashion and have them so close together was to have one with the arm around the other. And that's why this diorama is shown that way. There actually is some evidence supporting that interpretation. Are there other ways to interpret these? Sure, but that is one explanation. The other part of the trackway that I love is on the bottom here, where things get a little messy. You've got the smaller individual, right, left, right, left, right, left, and then there are these jumbled prints. Both individuals stop and they pivot and they face the west. And there's this sort of 3-4 count, and then they carry on. And for some reason, that moment, to me at least, humanizes them. This is this moment of curiosity. They didn't then run. I don't think they saw a predator. Something caught their eye. Something made them curious. And then they carried on. Footprints are these remarkably, really sort of, in some ways, poetic finds that we make that bring our ancestors back to life in ways that capture these moments, these windows into the lives of individuals that fossilized bones can't quite do the same way that footprints do. I think they complement each other really well. Okay, so how do we interpret the G prints? Well, this is the 1970s. This is a very linear idea of human evolution, that a chimp-like ancestor evolved into humans in a linear-like fashion. This is the time of the single species idea, that there was only one hominin species at a time. And so these footprints fit nicely into that sort of narrative of these ancient hominin footprints. And so what do you do then with the fact that there were these other bizarre footprints that were discovered 2 years earlier at the A site that were of something moving on 2 legs, right? You can't sweep them under the rug. You can't ignore the fact that these footprints exist. And so researchers at the time really struggled with this to interpret these footprints. They said, geez, we found the hominid ones already. They look really human-like. So what in the world are these things? And what they hypothesized was that these prints may have been made by one of these other mammals that occasionally walks on 2 legs. And that would be a bipedal bear. And this is the hypothesis that kind of stuck for about, it was about 30 years that we held on to this idea as a field. But one of the things we have up here in northern New England, we've got a lot of bears. We've got a ton of bears. And in fact, one of the world's experts on the behavior of the American black bear lives about 20 minutes from here. So we teamed up with him and we asked a couple of questions. And one of the questions was, how often do bears actually stand on 2 legs? Is this a common thing, common enough that at a footprint site that has thousands of footprints, you'd see bipedal footprints, but no other footprints at all of a bear moving quadrupedally? And so we used video data, hundreds of hours of video data, and asked the question of how often are bears bipedal? And the answer is about 1% of the time. And then of that 1%, how often is their bipedalism postural? Are they being intimidating or sniffing the air versus locomotion? And most of the time it's posture, 65% of the time. Only 35% of the time were they actually moving on 2 legs. And when they do move on 2 legs, how many steps do they take? And 86% of the time, it's less than 4, which is how many footprints there were at Laetoli, supposedly made by a bear. So you do the math there, and there is a less than 1%, less than 1/10 of 1% chance that that scenario would have played out at that site of Laetoli based on what we know about American black bears today. But we wanted to get their footprints. And so at this site that Ben Killam operates in Lyme, New Hampshire, he has a rehabilitation facility for bears who have been orphaned. Their moms have been hit by cars or abandoned them. And so they're taken in and they're rehabbed and then re-released. They're habituated to people, sort of. We got to be really careful around them. They're still bears. And what we did was we would entice them to walk on 2 legs in a muddy trackway using applesauce or maple syrup. They loved maple syrup. And so we would put some applesauce or some maple syrup in a bowl, and we would have them walk bipedally. And then we would collect their footprints and quantify their footprints. In addition to that, we were also looking at aspects of their gait. How do they move when they walk on 2 legs? Because when humans walk on 2 legs, we're able to balance really nicely on one because of the shape of our pelvis, the shape of our hips. But when bears do it, they wobble back and forth. So this graph here is showing you a quantification of that width of the stride, how much they wobble back and forth. So in yellow is the bear. So they wobble a lot back and forth. So really, really wide strides. Chimpanzees do the same thing. We collected data in Uganda at a sanctuary for chimpanzees. But, and again, it's about their hip structure. But humans and ancient hominins, this is Lucy and Lucy's predecessors as well, had evolved a pelvis where the musculature around the hip joint was repositioned in a way that they could walk on two legs, balancing on one at a time and not tip over and wobble side to side. So in yellow here is that quantification. So all of the footprints at Laetoli, including the weird ones from site A, actually had the feet really close together, which would be consistent with hip morphology from our ancestors, not from a bear. But in order to convince our colleagues, we needed to find these footprints again. And so in 2019, we went out to the site of Laetoli. This is one of the most gorgeous areas on Earth. It's just the east of the Serengeti, west of the Ngorongoro crater is stunningly beautiful. It's hard to get there. The road had washed away, so we had to rebuild the road. And it's, again, right on the edge of the Serengeti. And so you've got a lot of wildlife. So this is a tower of giraffes who is welcoming us. That's what a group of giraffes is called, is a tower, which is one of the best names for a group of animals I've ever heard. So how do we find these footprints? Well, it was a bit of a needle in a haystack situation, but we did have a map. Mary Leakey was very precise, and she drew exceptionally accurate, it turns out even more accurate than we could have known, maps of the site. And so this is the site A, and the footprints that we were searching for are these 4 bipedal footprints right here that are just west of elephant trackways. And then east of that are these tiny elephant tracks, baby elephant tracks. When we got to the site, we were a little dismayed. There had been a lot of water erosion, a huge section of the trackway, not the hominid trackway, but a huge section of site A had washed into a gully. And we had very little hopes that these were going to be there. We assumed instead that they had just washed away. Look, after 3.5 million years, water erosion cleared the sediment away, exposed the ancient volcanic ash that hardened and preserved these footprints 3.5 million years ago, but continued water erosion is going to take them from us. Footprints are so ephemeral, and they're these, you know, you're grateful that erosion gives them to you, and then erosion takes them away if you don't have a means of preserving them. But nonetheless, we dug, and we dug and dug and dug and dug, and after about a week of surveying the area, our field assistant, Callisti Fabian, hit the jackpot. And he found, indeed, this is an image of him discovering one of the footprints. We cleared that area, and indeed, we were able to locate those original footprints after, 45 years after they were first discovered. So erosion had not washed them away. Instead, erosion had pulled sediment from the hillside onto them and covered them back up like a blanket. So we did a lot of work uncovering the 4, and actually it's 5 footprints. Only one of them, really it's 2 of them, are really well preserved. The one that's exceptionally well preserved, we were able to compare back to the original images taken in the 1970s, and there was sediment still in there that they had not removed. And so we very carefully, with a thick bristled brush, removed a lot of that sediment, and we were able to get details of these prints that they were not able to get in the 1970s. In addition, we were able to use technology that was not available to them. So we used 3D laser surface scanners to get topographical images of these footprints, again, that can provide more detail to exactly the mechanics of locomotion that this thing was engaged with in when it was walking on this sediment 3.5 million years ago. And so new technologies allowing us to go back and revisit some of these old questions about these footprints. Okay, first, is it a bear? We don't think so. We don't think so at all. Bear footprints are very fan-shaped. They've got a narrow heel. Remember the wobble, the back and forth wobble? In this sort of ancient version of Cinderella, this foot just doesn't fit the slipper, right? This is a very different kind of animal making this print. And what bears don't have that this print clearly has is an enlarged big toe. So when we're able to quantify that and look at the size of the big toe compared to the adjacent digit in humans, which are here on the right, chimpanzees in the middle, they've got a big toe as well. Bears don't. So this one here is showing you that their big toe is the same size as the next digit next to it. If we were flipping the prints and it was digits 4 and 5, we needed to check on that too. Sure enough, it's more or less the same thing. And this footprint here clearly has an enlarged big toe. It's a primate. It's an ape, and it's an ape that walks on 2 legs, and that's a hominin, right? But, one last thing about the bear. You may be like, wait, bears in Africa? What are you talking about, bears in Africa? That should have been a non-starter from the beginning. There used to be bears in Africa. We do find fossils of a very large bear, a polar bear-sized bear that lived in Africa, most known from South Africa, but we do have fossils in Eastern Africa as well. However, at the site of Laetoli, there's not a single bear fossil. So we have about 20,000 fossils from this site, and none of them are actually from bears. So, okay, cool. It's a primate, it's an ape walking on 2 legs. That means it's a hominin. It's an ancestor of ours. We know, or extinct relative, we know that they were hominins in Tanzania at this time. They left us footprints, they left us fossils. It was Lucy's species. So might this foot also be, or this footprint also be from Lucy's species? We don't think so. On the left here is one of the best preserved footprints from the famous G trail that I talked about earlier. And on the right is a footprint from this newly rediscovered A trail. Those are really different feet. Now, different humans have different feet. We leave different footprints. And so we needed to analyze this in a more sophisticated way. So we asked the question, what is the likelihood that you would sample such differently shaped feet out of a human population, out of a chimpanzee population? And what we found was not very likely at all. This foot is much wider, and it's much more ape-like, much more chimpanzee-like actually, in how wide it is compared to its length. The big toe seems to be sticking out a little bit more than it does in Lucy and her kind. And we know a lot about Lucy and her kind. Again, we've got footprints, we've got foot fossils, we even have foot fossils of juveniles. So what we did was we sort of ran a simulation where we said, okay, what if we had, a couple of hundred human footprints, and we had a decent sample, say 50 or so chimpanzee footprints? What is the likelihood that we would find 2 footprints that differed from each other as much as these 2 fossil footprints from the site G and site A? And we found not very likely at all. In fact, these 2 footprints differ as much from each other as a chimpanzee footprint, that's what's shown in yellow, does from a human footprint, and that's what's shown in gray. And all the other lines are the other Laetoli footprints from site G, and there's another site called site S. So they all clump together. They're all similar to one another, but this other footprint from site A is really strange. But it starts to make sense when you incorporate it in with other fossils that have been discovered. I mentioned Johannes Haile Selassie a moment ago. He actually is in Ethiopia again. There's a peace agreement there, and so it's safe to return to some of those fossil sites in Ethiopia, thankfully. He's a fossil magnet. He's amazing at discovering these. And a couple of years ago, he discovered a fossilized foot in Ethiopia that's the same age as Lucy and her kind, and roughly the same age as the Laetoli footprints. But that foot has anatomy, morphologies really, that are very different from the foot of Lucy and her kind. So there were 2 different species of hominin coexisting at the same time and even walking in slightly different ways. And this is an image that was done from a Scientific American piece that I just had published. And I love this graphic. I didn't do this graphic. The folks there did it. And I absolutely love it. because it shows over evolutionary time, starting from the top down, the last 7 million years, that there are all these different kinds of feet. And when you have different kinds of feet, well, then you use them in different kinds of ways, and you actually walk from point A to point B in biomechanically different ways. And so we, again, think of evolution, sometimes we simplify it and we think of it in this linear manner, and a chimpanzee slowly evolving into a human. And as I talked about earlier, not only is the common ancestor probably not very chimpanzee-like, but along the way, there were all these different experiments going on in how to walk, in how to be a bipedal ape. And so what all of our new discoveries have been showing us, and John will illustrate this even better in a couple of weeks, all these new discoveries that we've been making in our science have been shocking, honestly. They've been really surprising. And they've shown us that the story of human evolution is much more complicated, and frankly, it's much more interesting than I think any of us could have imagined. So thank you very much. There's some folks to thank, of course, and then I'm looking forward to chatting with you about whatever questions you have about upright walking or Laetoli or fossil discoveries or any of my friends behind me, anything at all.
TIES is the Teacher Institute for Evolutionary Science. We provide free resources for teachers in K through 12 classrooms, public and private schools. And we have a website, it's tieseducation.org. We're also on Twitter and Facebook, and we have a new YouTube page where you can see post webinars, and you can also see free classroom resources at all of those websites. If you go to our website or if you go to our Facebook page, you will see upcoming webinars. We have 3 more for this semester, and then we're going to take the summer off, and then we'll be back in the fall. We have 1 in April, and then we have 2 webinars in May. And I just added the May 3rd webinar today, and he is joining us now, John Mead. He's going to be talking about hominoids. And Jerry, you did a great job, but every time John presents, I get goosebumps because he's just an average teacher. You know, he's just a normal teacher, just like the rest of the TIES group, and he is really invested and he gets to do all these really amazing things. And I'm promoting that webinar specifically because if you enjoyed Jerry's presentation, that's a nice tie-in to hominoids. All right, so there you go. And remember, you should register on the website or through Facebook. All right, one thing about TIES, Teacher Institute for Evolutionary Science, our motto is teachers helping teachers. We provide resources based off of other teachers' references and that they've already used them in their classroom. So we are looking for teachers who can share their expertise with us on advice for addressing common evolution misconceptions like the March of Progress. We're also looking for teachers' advice on how they address that evolution is a theory, just a theory. And then we're also looking for teachers who can give us some advice on how to make children comfortable who are told that evolution is against their religion. Now, every webinar, I have this slide and I'm asking for TIES tips. If you are a teacher, I'm actually talking to you. We actually do need TIES tips. We want to create this beautiful free resource on YouTube and our website. We're just looking for a couple of minute videos, and John Mead has presented his TIES tip, and Bertha Vasquez, the director, of course, has submitted her TIES tip, but we're looking for other teachers all over the country. If you've taught for 1 year or 33 years, we could use your advice. All right, I keep saying all of our resources are free. All of our resources are free except for one, and that is our book. And that is because we have to pay the publisher to print the book, and we would be actually sending you a physical book. Here it is, it's beautiful. We just published it last year. It includes about 10 different teachers' experiences, and if you add all those up, that's hundreds of years of experience. And What's really cool is there's QR codes in the book that direct you to the website. But if you don't want to purchase the book, or if your school district cannot afford the book, you can just go to our website and you can see all of the resources that the authors recommend. TIES is part of the Center for Inquiry, and under that we have some other educational offerings. One of them is Science Saves. Just like TIES, Science Saves is created by teachers for teachers, and we have lots of different free lessons. They are in elementary, middle school, high school, language arts, science, math, because science infiltrates all of our lives and all these different subjects. Something exciting about Science Saves is that this year, and for at least the next 3 years, we will be giving away a lot of money for seniors in high school going into college. And the way that they get up to $10,000 in a scholarship is by submitting a 30-second video about how science has improved their lives. First place gets 10,000, second place gets 5,000, and then it goes down from there. The deadline is May 8th, and that's pretty easy. A 30-second video can make you a lot of money. And that money you can use, you could put it in a mutual fund. You could use it to buy food. You could use it for room and board. You'll find out if you're the winner after you get accepted to your college, and you can use that money however you deem fit. So how has science helped or improved your life? It could be how you have a little asthma inhaler. It could be how you have an artificial limb. It could be how you take Benadryl. It could be any aspect of how science has improved your life. All right, the first question, Jerry, you can unmute yourself, very good, is from John Mead, your fellow presenter. He asks, what, if any, is the age difference between site A and site G prints?
For all intents and purposes, they were made at the same time. So the way we understand the origin of the Laetoli footprints, it's really amazing. There's a volcano that erupted. East Africa is very tectonically active, lots of volcanic eruptions. A volcano erupted, laid down this bed of ash, and then it rained. And the ash had a particular chemistry that mixed with the water. It then took on sort of the properties of like just freshly poured cement. And then animals walked through it. The sun came out, dried up that volcanic layer, hardened it into the exact sort of form of these footprints. And then the volcano burped again and laid down another bed of ash, and then again, and another bed of ash, and again, and these little layers that then covered up those footprints. And there are actually 14 layers that you have to kind of penetrate through to get to the footprint layer. There are footprints in some of those other layers. It's not like the animals stopped moving, vanished from the area, but most of the footprints are concentrated in the same layer. And that layer, we think, is capturing a moment in time that's probably several hours, maybe a little longer, maybe a couple of days, but most people think it's just a couple of hours. And so the A prints would have been made roughly the same time as the G prints. But that site is 2 kilometers away from the G site. And so I don't think those hominins were moving together. There is one other site called site S that's right next to site G. And I think those hominins, they're moving in the same direction. They're in the same layer. I think, look, primates are social. I think there's going to end up being a big group of them. And it's amazing to me at this site how much has not been excavated. Like there are these little pockets where you get the footprint layer, and then these vast areas where the footprint layer is still buried underneath sediment. So we're going out there this summer with some ground penetrating radar, because we know there are footprints under there. So we're going to see if we can pick up some of those details using ground penetrating radar. And if we can, then we're going to survey a lot more of that area to try to find, where are these hominids going, and can we pick up the trail again at other spots. So it's going to be exciting.
All right, we do have a question from Vivian, who's a middle school student. And she asks, how long approximately did it take for the evolution of walking on 4 legs to 2 feet? So I know you kind of mentioned that we're still
Yeah.
We don't even know if we did that or we descended from trees. Or
Yeah,
came
we're
out.
still trying. Yeah, we're still trying to figure that out. It's a fabulous question, and it gets to sort of the, one of the things that we argue about as evolutionary biologists is the pace of evolution, and whether it happens gradually or if it happens in these fits and starts. And my answer usually to that is yes. It depends on the animal you're talking about. It depends on the trait. It depends on the time scales you're talking about. But one of the things that I find fascinating about the earliest hominids that we have evidence for is that they show these hints in their pelvis and in their foot that they're able to walk on two legs on the ground. Not the same exact way you and I do, because they still have a grasping big toe and they still have hamstring attachments on their pelvis that would allow them to really propel and climb exceptionally well. They've got long arms and they've got curved fingers. So they're very comfortable in the trees. But then when they're going to move from one food patch to the next, as animals need to do, instead of moving on four legs like a chimpanzee would do, they go from point A to point B on two legs. But I think, and this is a hard thing for us to figure out, but my guess is they spend most of their time in the trees. And then when they're trying to just get from point A to point B, that's when they're moving on their two legs. And what's amazing is that the fossils we have that fit that category of things mostly in the trees, but then occasionally on two legs, occupy a very long period of time, from about 4 million years ago to back to about 7 million years ago. 3 million years of that being the best way for this early hominin to be moving is really to stay in the trees most of the time. A lot of predators out there. And it's around 4 million years ago that we see what appears to me to be a pretty sudden shift to being really good on two legs, because you can't afford to be lousy at it. If you're lousy at it, you're going to be picked off by predators and you're going to go extinct. So I think at that point, you're getting very intense selection pressure to have anatomies in the knee, the pelvis, and the foot to be exceptionally good at bipedalism. Otherwise, you go extinct, right? And a lot of these did, right? The ones with the grasping toes climbing the trees, a lot of them vanish in the fossil record at that point. So what's driving that? What's driving that is a drying and cooling of Africa and the spreading of grasslands. So the forests are beginning to retreat, ancestors of chimpanzees and gorillas presumably living there, and the grassland expansion is creating this new niche, this new environment where moving on two legs efficiently is not a bad way to survive, especially if you're doing it during the heat of the day when other animals are asleep. And that's when you start collecting your food, but you can't be a picky food eater. You need to expand sort of your diversity of your diet. And we see isotopic evidence of that happening at that time as well. So humans today, humans today around the world, we eat everything, right? If it has DNA in it, we've tried it as a species. As an individual, maybe not, but as a species, we eat everything. That's very different from other primates. So when did that start? I think it started around 4 million years ago as we evolved much more efficient bipedal locomotion on this changing habitat. So the answer to your question is complicated. We don't really, know. We're still trying to figure it out. But I do think that 4 million years ago is sort of the 3.5 to 4 million. That's that key window of this shift from something that's mostly in the trees to something that now is mostly on the ground. And then all the other things that follow from that.
To learn more about human dietary needs and our recent ancestors, you can watch our Kevin Hunt webinar on chimpanzees, because he does talk about their diet and bonobo diet.
Awesome.
Jared, can you tell me how you know about that hamstring tendon or muscle connection when you're just looking at fossils?
Yeah, so
fossils,
so here's a fossil pelvis. This happens to be Lucy's pelvis, so a 3D printout of it. The original's in Ethiopia. The hamstrings insert right on this chunk of bone right here called the ischial tuberosity. And what we do is we think of bones as levers. That's kind of all they are, is levers for muscles. So you can apply physics and principles of mechanics to bones, that if this chunk is further away from this axis of rotation, from this joint, the hip joint, then it's going to be more efficient and it's going to be able to produce more power. And in chimpanzees, that's exactly what we see. And in early hominins, in Ardipithecus, for instance, that chunk is really far away from the hip joint. It's in a very ape-like position. But what's happened over the course of human evolution is that this ischial tuberosity has folded and bent up closer to the hip joint as we've become a quad-dominated walker. Our hamstrings are important. They're important for sort of regulating speed and making sure we're not clunky walkers, but we're really quad-dominated when we're walking. The quad is what prevents knee collapse when you're standing on a single knee. And so that muscle then, the attachments for that muscle, at least one of them, is right here. And that becomes prominent in these early hominins. It's not prominent at all in chimps. So these little bumps on bones reveal so much. You know, it's like this wonderful little detective story when we find a fossil and look over all these tiny little bumps and grooves and use that as evidence to sort of, you know, and what we understand about comparative anatomy in animals today to try to piece together how they were moving.
So you have beautiful fossils, or at least skulls behind you. And right now we have a lot of middle school and high school students watching, but when this gets published, we'll have a lot of teachers watching. Great. And can you tell me if you know of any websites or resources to go so they can print out a 3D skull or fossil, because those museum quality replicas are hundreds of dollars.
Yes, they are. Yes, they are. I'll give you a couple of sources. One is called Morphosource. Morphosource.org. It was established by my colleagues at Duke. And it's a free repository for 3D fossils. All you have to do is put in your information. They don't require a credit card or anything like that. And you get a username and a password, and then you can download these to print. Sketchfab actually has a lot of hominin fossils on there as well. I was just looking at a few today on Sketchfab. And then if there's anything you need for your teaching and you can't get it in some other way, email me directly. I have made 3D laser scans of the majority of my collection, and I'm more than happy to share scans of fossils, understanding that sometimes there are restrictions against sharing some fossils because of rules in the countries where they've been discovered, and I have to abide by that, of course. But you know, I am more. I really am passionate about you know, that these fossils should not be, you know, under lock and key and only held and observed by scientists. You know, if we're going to really understand human evolution and inspire the next generation of students who are going to be excited about human evolution, they need to be able to hold these things in their hands. And so I lose my mind, and I just cannot understand when colleagues of mine find a fossil and then don't share it with the world, when they sort of hide it. It's just bizarre, and I'll never ever understand it. And so I'll do whatever I can to overcome that.
John Mead adds africanfossils.org is another great site. There you go.
Absolutely.
I think we have 2 more questions, Jerry. One is from Helene, and then also Gordon. Can you tell us a little bit more about the hypothesis about terrestrial and versus arboreal? But then Helene added, what about the enlarged big toe in the majority of hominids? Does that help your hypothesis?
Yeah, so if you look across mammals, you look at your dog or your cat or footprints made by a squirrel or something like that. There's a lot of variety in digits and sort of the arrangement of digits. But primates are pretty unique in having a grasping big toe that sticks to the side and grabs things like your thumb does. So grasping hands and grasping feet are characteristic of primates. So these are the monkeys, apes, and also lemurs and lorises and tarsiers and things like that. And there are some really great hypotheses as to why that's the case. If you look at how your dog walks or how a horse walks, it's usually left side then right side. So they go left foot, left hand, right foot, right hand, left foot, left hand, right foot, right hand. And that's what's called a lateral sequence walk. Whereas in primates, what we do is diagonal, we do opposite. So we do left foot, right hand, right foot, left hand. And when we do that, if you're in the trees, say, and you imagine yourself sort of positioning your body in that way, you're going to get kind of unbalanced. And what we think is going on is that that's going to help them with their reach as they're reaching out and testing branches and grabbing onto fruit or grabbing for insects. But that only works if their back legs are grabbing onto something. And that only works if you have a grasping big toe. So we find very early on in the primate fossil record, right after the extinction of the dinosaurs, 65 million years ago, grasping feet in primates. And then in apes, by 20 million years ago, when we find the first apes, one of the things that characterizes apes is they don't have a tail. So chimps and gorillas and orangutans and gibbons and humans, right? We don't have tails. So if you're in the trees and you want to balance, think about any mechanism we have for balance, usually, having a pole for a tightrope walker, for instance. You want to have something that you can extend out to balance. And by losing the tail, we actually lose that ability to balance in the trees a little bit. So one of the hypotheses there, the arguments, is that that's when you start seeing the really exaggerated long arms, curved fingers, and a much more powerful grasping toe. So apes, again, retain and even enhance this grasping big toe. Now, the way evolution works is that you can only evolve sort of pre-existing structure. It's a tinkerer, right? Modifying what's already there. So we have this big grasping toe. And as bipedalism becomes an important form of locomotion, what we see is that the early bipeds are keeping that grasping toe to climb, and they're pushing off the outside of the foot. But if you, the next time you're sort of walking around, if you just keep your weight on the outside of your foot, you can't take a long step. You can't really generate propulsion. So when that becomes really important in our ancestors, and again, I think it's about 3.5 to 4 million years ago, what you see is the loss of the grasping toe. The big toe comes in line with the other digits. And in fact, we think maybe the other digits come in line with the big toe. That might be how it's happening. Everything stiffens up, right? But then there's weight transfer to the big toe, and that's where the main propulsion is happening. So we've recruited, I say we, through natural selection, this big grasping digit that apes have has been tinkered, tweaked, modified, recruited into this new role as being the main axis of propulsion when we're walking. So the big toe remains important. It's not for grasping anymore. It's now for bipedal propulsion. So it all fits together. It fits together quite nicely. Exactly, could that same scenario have played out from something on the ground, like a knuckle walker evolving into a biped? Yeah, absolutely. Because then you would still have something with a grasping big toe evolving bipedalism. What we really need to tease out those two ideas are more fossils. And it's a common claim in our field, oh, you just need more fossils. And it really is true in this case that we don't know much about what an 8 million year old African ape looked like. What did the ancestor of chimpanzees look like? We need a Lucy for gorillas. We don't have one. We've got very few fossils of chimpanzees and gorillas. Really nice fossils from humans, very few from our ancestors, our cousins, sorry. So we make the mistake of using them as substitutes for our ancestors when they may not be at all, right? They almost certainly have evolved quite a bit themselves. We just don't know how because we don't have a fossil record for them. We will, we're working on it.
Do we know why it would have been disadvantageous to have a tail? Do we know why they lost the tail?
So one of the really cool things about, again, it's a great example of how evolution works as a tinkerer, as something that sort of re-recruits a pre-existing structure. I think of our body as like a big junkyard of things that have been modified and tweaked for other purposes. The muscles of the pelvic floor, and this is true of all the apes: gibbons, chimpanzees, gorillas, orangutans, bonobos, humans. The muscles that make up the pelvic floor, these are the muscles that keep your reproductive and digestive organs in you, because gravity is pulling them down, right? And there's a condition known as prolapse that can happen. Those muscles are the same muscles that your dog uses to wag its tail, that a monkey uses to as a prehensile tail, right? So we still have those muscles. They've just been re-recruited. And what do they anchor to? Many of them anchor to the coccyx, which is our vestigial tailbone, right? And so we still kind of have the remnants of an ancient tail. And we talk about it as being non-functional. That's not really true. That coccyx is pretty important in anchoring those really important muscles. And so why did we lose the tail? One of the ideas, and I think it's probably true, is that apes, when you compare them to monkeys move around on all fours like a squirrel, like a dog, like a cat. Apes, though, they're upright. They're very vertical. Now, we've taken that to an extreme and we walk on our two legs, but gibbons are very vertical when they swing in the trees. Orangutans will do what we call quadrimanous walking, where they walk in the trees upright. Chimpanzees climb trees in a very upright way. Gorillas will stand up, sometimes even walk on two legs. So it's the apes that are very, what we call orthograde, very upright. And when you're upright, gravity is going to pull stuff down, right? And so the tail then becomes sort of the raw material from which you can then build a pelvic floor to support the organs and prevent them from prolapsing. So that's one of the ideas, one of the hypotheses about the loss of the tail. And we know it happened about 20 million years ago. That's the timing of when apes evolved. It's about 20 million years ago. And the fossils we have from that time period already show an ape without a tail. So taillessness is one of the earliest ape anatomies.
Do you know if it's called brachiating? Is that what gibbons do?
That's what gibbons do. That's right. It's kind of like running. You know how in human running, there's an aerial phase. You're on one leg and then you jump off that leg. And so you're flying. In brachiation, there's an aerial phase. You're swinging and you actually will leap before you get your next swing. And gibbons do that. And then young chimpanzees do that, young orangutans do it, young gorillas do it. But once they get big gorillas can't do it. Big orangutans can't do it anymore. But brachiation, yep.
I remembered something from my primate undergrad class. Jerry, if you have time, we have two more questions, comments.
Sure.
This is a good one. Do we believe all of the hominids to be slim and tall? I know Lucy was only like 3.5 feet. Do we have any evidence of fatter individuals waddling rather than walking?
So I've got a Lucy back here, and she fits in this drawer. Like, she's tiny, and we know she was an adult. She has her wisdom teeth, and so she was a young adult. Her wisdom teeth are not very worn. And then this standing skeleton behind me is of an individual known as Carabo. This is an Australopithecus, like Lucy was, but lived about 1 million years later in time in South Africa. An amazing story of this discovery that I would imagine John will go into a little bit. This was found, first fossils were found by a 9-year-old kid who was with his dad, who was a paleoanthropologist searching for fossils. So that's another serendipitous discovery in the history of our science. We got a lot of those. Makes you wonder how much we haven't found, right? Also quite small, about 4 feet tall. So Lucy is a little less than 4 feet. So for Australopithecus, what we find this time period, 4, 5, 6, or even more recent, I should say, 2, 3, 4, 5 million years ago, is that the what we think are females, the smaller individuals, tend to be about 4 feet, and then the larger individuals, who are often thought to be male, hard to know for certain on that, are usually about 5 feet or so. The one that had broken his ankle, big guy, Katanumo, I mentioned, he's about 5.5 feet tall. So he's one of the biggest that we've discovered. So he's
Were
quite
they
remarkable
bulky,
in
like a gorilla?
size. Well,
Or
so
can we?
it's a great question. What we can see in the shoulders and the arms are big attachments for muscles. And so I showed a slide of sort of an artistic version of an Australopithecus, and they're jacked. Like they're really strong in the upper body. And I like that reconstruction because the fossils to me show really strong muscle attachments in the upper limb. And they've lost a lot of the climbing adaptations in the lower limb. So if they're going to get up into a tree, which they need to do to stay away from predators at night, so they had to have gotten up into a tree, they would have had to have pulled themselves in a very in a way that we would have needed to, right? Using our arms, not so much our legs and our feet, because our feet aren't grasping much anymore. And for Lucy, you know, in her kind, neither is she. So body size is an interesting thing. It's hard to know for certain, but you can use the size of the bones compared to the size of the bones of known sized individuals today to work out weight, to work out height. We look at sort of body proportions, arm length, leg length. The hips would suggest that they were not skinny, that they actually were a little wider. And there are some arguments about their digestive organs being, at least at Lucy's time, more developed than ours today, in the sense that they could digest more raw vegetation. When you're going to eat a lot of raw vegetation, you want to have a pretty well-developed digestive system. Think of a cow, right? Or any ruminant that has, you know, multiple stomachs. You know, gorillas live in a salad bowl and eat vegetation all day, and they've got these big bellies, and that big sort of vat of bacteria breaking down the cellulose that's in plants. And we don't have that so much. And so around 2 million years ago, you start to find evidence for a slightly different body shape, a leaner body shape. And we think that coincides with some dietary changes, maybe the incorporation of a little more meat, a little more marrow, but probably also the invention of cooking and the use of fire in order to serve this external digestive role. You know, think about digesting a raw onion versus a cooked one, you know, or a raw potato versus a cooked one. It's a very different experience. And our digestive organs probably evolved, you know, coincident with that.
We have a comment and a question. Somebody said, we'll say Jelko, I'm so sorry. He's here every webinar. I need to learn your name. I didn't know there were bears in Africa. It is often mentioned that they are not there, so I assume they were never around. That's correct. They were there. Just like camelids evolved in North America and then went that way. Yeah.
Right. Exactly. Yep.
All right. And Betsy Ann asks, does the arch, shape, and height say anything about walking in these fossils? And that's going to be, unfortunately, the last question of the night.
That's okay. It's a great one. So, Betsy Ann, if you asked me that a year ago, I would have said, yes, absolutely. I collected all these footprint data and here's what we found and blah, 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 right? I was totally wrong. There was a study that came out by a close colleague of mine about 6 months ago. And what he showed, and he showed definitively, it was a really elegant study. He showed that what you leave in a footprint, what looks like an arch in a footprint, is actually weight transfer as you're walking. It's your propulsion. And whether you have high arches or low arches, it's the manner in which you walk. It's your propulsion that actually is the driving factor in determining the characteristic of your footprint, not your arch height. And it means some early papers that I wrote on this are not right, or not as right as I thought they were. We don't throw them out completely. There are some things I can salvage from them. But so for years and years, we looked at the Laetoli footprints and we said, wow, look at that arch. There's an arch there, but it's not quite as high as the average arch in humans today. And that's wildly variable from person to person. It can even change over the course of your lifetime. But what we now think about these footprints is that that's telling us about propulsion and how they walked, not necessarily what their feet or how arched their feet are. We can tell that from the bones, though. From the bones, we still debate about this, but from the bones, generally what we have found is that their feet are arched compared to a chimpanzee's, but not as arched as most humans have today. And there are some scholars who have thought a lot about the arch and would argue that that's because they weren't as capable at running, as this sort of distance running, as the genus Homo erectus, and eventually Homo sapiens could do. That the arch is this energy storing mechanism when you're barefoot running.
Bertha Vasquez, our director, has a t-shirt that says, aspire to be less wrong. Or I aspire to be less wrong. And then our Science Saves program is all about how it is okay for scientists to be willing to adjust their theories and understanding based on new evidence, because that is how science works.
It's so, science collapses, it falls apart when you have people who dig in their heels and are unwilling to modify their interpretations of, say, the fossil record or anything based on new evidence. Why are we doing what we're doing if new evidence we're just going to ignore? So, as a human, it's hard to admit you're wrong. But as a scientist, and scientists are human, so I'm not sure where I'm going with this, but as a scientist, like I get great satisfaction sometimes in realizing that I've discovered something that the old Jerry DeSilva thought was different. I don't know. I love changing my mind. Changing my mind I find to be just this really satisfying thing when the evidence compels me to do so. But it's, I don't know. It can be difficult still to say, well, I was wrong, and you have to, then sort of not retract your papers, but to tweak them and modify them. It'd be hard.
All right, very good. Thank you so much, Jerry. And we want to remind all the viewers that your book, First Steps, How Upright Walking Made Us Human, is available now. And thank you also for everybody who attended live. And everyone else, have a great night.
Thank you.
Bye, everyone.